highly correlated. Can we just drop one of them? I think it will be a very bad idea, because case and distance convey complete different type of information. If you drop case, it's not a good idea. If you drop the distance, it's not a good idea. So we wanted to keep both of them. To keep both of them, we have this multi-collinearity problem. They are highly correlated. So we cannot drop it in this case. Well, fortunately for this example, there's an easy way out. You can collect more data at a certain point to break the correlation or to reduce this correlation. So, second way is we can try to re-specify a model. So suppose you have two variables, two regressor variables, length and breadth. And these two are highly correlated. Well, if you have a linear regression model with x1 and x2 as regressors, then you will have a multi-collinearity problem. So what we can do is, instead of using x1 and x2, maybe we can just use x, which is the product of this. Look at the area instead. So when we look at this, we got rid of the multi-collinearity problem. So some of these regressor variables can be combined together in some meaningful way to reduce this multi-collinearity problem. So that's one way. So what's way number one? Just drop one regressor variable. Look at the mileage data. There are so many of them. They are convey very similar information. Yeah, like the thrust, the power of the engine, the mileage. All these are very, or the capacity. They are all very highly correlated. You can drop them. And the third way is to use rich regression. So rich regression is an interesting idea. So to understand rich regression, let's try to understand what is a rich. So this is a rich. You can see two people there. Yeah. So what is a ridge? It's a long, narrow mountain top. Yeah. And that's a ridge. So I think it'll be fun to climb a ridge, I wish I am one of the two, instead of in the lecture theater. Soon I'll be going somewhere, maybe. So, well, we don't have to go too far to climb a ridge. We have a Kent Ridge here. It's called Kent Ridge Campus. There is a ridge here, right here. We are somewhere, this is the sports hall. We are somewhere here. You can go up here. And then there's a long, narrow ridge, Yeah, you can walk the whole length of it. I think it continues all the way to the science park. That's why this campus is called Kent Ridge. Now, what's ridge to do with reducing multi-collinearity? Okay, so we need to understand how, why would the regression coefficient have high variance? Let's try to study. Researchers had this multi-collinearity problem, and then they scratch their heads, trying to find ways to reduce this variance, because that's the effect of multi-collinearity. So some researchers, started looking at this matrix carefully, X prime X matrix, So this is the X prime X matrix. And the diagonal elements, I call it the ridge of X prime X. Why do I call it the ridge? Well, we'll understand it soon. So, so what happened here is you can find, you can find beta hat simply by inverting this matrix. And find the regression coefficient. And another thing to note is the variance of beta hat is sigma squared X prime X inverse. So it has a lot to do with this X prime X matrix. Yeah? See, this matrix, we get beta hat and we get variance. Now this matrix is non-singular most of the time. But when you have two regressor variables, let's say they are highly correlated, then you have two rows that are almost identical, or two columns that are almost identical. And that makes X prime X matrix ill condition. Ill condition means almost like singular. Yeah. When it is ill condition, this will become very large. The elements of this will become very large. And so you have this, the variance will explode. So let's look at an example, a more concrete one to see how this regression works. So let's start with a simple matrix here. A, 2, 8, 3, 15. So the denominator here is 2 times 15 minus 8 times 3. So no problem. 30 minus 24, 6, 1 over 6. So A inverse exists. What about this example? 2 times 12, 24. 8 times 3, 24. So here we have 1 over 0. That means A inverse does not exist. Okay, so that is a singular matrix. A is singular. Now what if, so why would it be, okay, it's singular. So how can we make it non-singular? So that's what researchers were thinking, when they try to come up with this ridge regression method. Well, you see, if I add this constant to the diagonal elements, k, add k to each of the diagonal element. So I will get 2 plus k here, 12 plus k. All right, so that's A plus k times the identity matrix. Now what is the inverse of this matrix now? The inverse of this matrix is this. Well, if k is 0, this denominator is 0. So it's singular. But because we've added k to it, k is positive, so some positive number, then the denominator becomes positive. So in this way, we now have a non-singular matrix. In other words, if you strengthen the ridge of this matrix, you will get a non-singular matrix. Yeah? The more you strengthen it, the better it is. The more non-singular it becomes. Yeah, you move it from singular to non-singular. So simply by strengthening the reach of a matrix, you can help to reduce this problem of inflation of the variance of the regression coefficient. So that is the basic idea of rich regression, is by strengthening the reach of a matrix. So once researchers realize that they can, strengthen the reach of a matrix to make X prime X matrix less ill conditioned, then they come up with this rich regression method. So ordinary least square regression simply just do this. But if you have regressors that are dependent on each other, highly dependent, then this matrix become near singular, and that means this matrix is ill conditioned. So the inverse will contain very large elements, and so it causes problem to the estimation of beta, and also in the variance of this beta hat. That's why when we try to use this ordinary least square model to make prediction of response for the acetylene data, we find that we get nonsensical answers. We got negative conversion. The percentage conversion should be non-negative, but it gave us negative numbers. Do you remember in the last lecture? Now in rich regression, actually the idea is very simple. Well, this is ill condition, assuming that they are regressors that are highly correlated. So if I invert X prime X matrix, I get very large elements because it's ill conditioned. So I strengthen the reach, and I use this as my estimator. So this is called reach estimator. Well, I have this term here. And how did it work? So this is the main idea of rich regression. Simple idea. And then you just have to now study the properties of it, see how good it is. So researchers went on, and study the properties. So we will go through this. Well, number one, the rich estimator is still a linear transformation of, it's a linear transformation of the ordinary least square estimator. This is called ordinary. And this matrix here, I call it ZK, make it more compact. And so what's the price to pay? Now we now should have, the rich estimator should be more stable, and the variance should be much smaller. But what's the price to pay? Now the price to pay is this. There are a few things to pay. This is one of them. Now expectation of this is ZK beta, which is not beta, unless K is 0. So what happened here is you have a bias estimator. Hopefully the bias is small enough for us to accept, then we are fine. The bigger the K is, the bigger is the bias. The smaller the K is, the smaller the bias. What about the variance? Well, the variance you can work it out, right? The variance. I will just show you the method. You can verify that this is true. So this is, looking at this. So this is ZK, variance of beta hat, ZK prime, and this quantity is sigma square x prime x inverse. So that is the variance of the variance covariance matrix of the rich estimator, which you can simplify to this. Okay, try this. Make sure you can get this. All right. Now, the next thing, point number four is, I want to study the mean square error. So in probability or statistics, you have learned mean square error. So what is mean square error? Suppose beta is a scalar quantity. I think you have learned the scalar version of mean square error. And beta hat, also a scalar, is an estimator of beta. And the mean square error of beta hat is defined to be this: the expected value of the square of the distance between beta hat and beta. That's the definition. 3 lines mean defined to be this. And this expectation can be written as the variance of beta hat plus the bias square. So this is the expectation of beta hat, this is beta. So the difference is the bias. Okay, now, what about the case when beta r is a vector? So now, when we do even simple linear regression, we have two beta. So beta is vector. So how do you define mean square error of a vector? Similar. It's defined to be the expected value of the square distance between beta r hat and beta. So we generalize it to a vector. And this can be written as this, trace of this. I checked this. Let me just say that. So for this result, you can check chapter 3b, page 3, for operation on variance. Now for this one, you can check chapter 7c, page 26. So it will show you how to find expectation of the square distance between beta r hat and beta. So this part is the trace of this. The trace of the variance. So the variance of beta hat is actually just the sum of the diagonal elements, okay? And then here is just the bias of each one of them squared. Okay, so that's what happened. And you can actually try and prove this. A little bit involved, but it can be shown. Can be shown to be this. Now, so this part here represent the variance, the variance of each of these rich square estimator. Yeah, the variance. And this part here represent the bias. So the second part represents a bias, the total bias. And this lambda 1 up to lambda p, of course, are the eigenvalues of x prime x matrix. Well, so now we want to study the effect of K on the variance, on the bias, and the mean square error. So we know we need to choose a K that is big, okay? But we don't want it to be too big. Let's see. What happens when K goes up? When K goes up, what happens? If you choose a bigger K, then the variance will become smaller. Do you see? Well, remember, we want rich estimators with small variance, right? That's the reason why we strengthen the reach of the X prime X matrix. So if you strengthen it with a K, the total variance will come down. The larger the K, the smaller is the variance. So it's a good thing to have a large K, because they will help us to reduce the variance. That's why we started using rich regression. But then, now look at this part. K square is here. So if K is large, what happened to the bias? The bias will go up. Although the variance has come down, but the bias has gone up. So you're not using an unbiased estimator anymore. You have a biased estimator. Now, some of you might ask this question. K squared goes up. But what about this part? Beta transpose times this matrix. This matrix inverse times another one of it. So it's minus 2 and a beta. So how do we know this is not negative? How do we know this is non-negative? Can anybody tell me? Here it's very obvious. These are all positive. So if K goes up, this whole thing will come down. The variance will come down. So what about this? This go up. I say the bias go up. But what about this? It has to be non-negative for what I say to be true, right? So how do I know this is non-negative? Can anybody verify this for me right now? The verification is very simple. Why? So now, I claim that this matrix, when you multiply them all together, will give me a non-negative value. Why? Anyone? So you might, if I set this as an example of problem, you might start trying out with a 2 by 2 matrix, right? To see if it works. You won't find anything. It's not easy. How about 3 by 3, 4 by 4? How do I ensure that this is non-negative? Can anybody tell me why? I know this is non-negative. Why? As I say, this means the inverse of this matrix times the inverse of this matrix. That's why I have a negative 2, all right? Okay, let me tell you why. This is positive, right? Or non-negative. This quantity must be non-negative. The reason is very simple. Because this whole thing is this. Is the sum of the bias square. What's the sum of the bias square? The sum of the bias square is non-negative. So, this is non-negative. This is non-negative, so this must be non-negative. Okay? So, we now know as K increases, the variance will decrease, but the bias will go up. So we we pay a price for it. We managed to reduce the variance, but the bias goes up with K. That means we shouldn't use a K that is too large. So that's one thing to note. Now, let's look at this graph that compares two estimators. For this graph A, I have an estimator that is unbiased. So here's better. My estimator is unbiased. All right, so it's unbiased, but the variance is large. That means, think of this as the ordinary least square estimator. It's an unbiased estimator, as we all know, but the variance is large because of multicollinearity. Yeah? And so mean square error will be large because one of the components of mean square error is large. Now, you know, in statistics, we always try to look for unbiased estimator. Why would we want to use a biased estimator, right? But well, there are cases when a biased estimator might turn out to be a better choice than an unbiased estimator. So look at this estimator. Beta hat star is biased because the expected value is here. The true value is here, expected value is here. But if this biased estimator has a small variance, that means here, okay? Then the overall mean square error could be small. In fact, if you look at this, you know, this is just sampling. If I take an estimator of beta hat, I could end up with a beta hat right here, which is quite far from the true value. Here, I take one value, maybe at most is here, because the spread is small. So I have a smaller distance. So end up, my beta hat is closer to the true value. Even though I know it's biased, but it might give me a value that is closer to beta than this one. So if you get a value here, then disaster for you. Yeah? So, so sometimes when the variance is large, it's not a good idea to use it. Maybe it is better to use a biased estimator. Okay, let's now go to point number 5. What is the sum of square of residue for the rich estimator? Well, according to definition, it is this one. And you can show it actually quite easily that it is related to the sum of square error for the ordinary least square. So this is SSR for the ordinary least square plus an extra term here. So how do you prove it? I'm just going to show you something. So here you subtract x beta hat and x beta hat. So 0, right? So do the same thing. Do the same thing here. So you introduce this term into the vector there, and then expand it out. You will get this. Now, so what happened now? As k increases, the SS residue will increase because the bias will increase. See, this is a bias. Here's a bias. So if k increases, bias increases, and so excess residue will get larger and larger. So this means it is not a good idea to use a large K. So by strengthening the ridge, in summary, by strengthening the ridge of x prime x, we actually have an estimator with smaller variance, but we pay a price. The ridge estimator is biased, and the sum of square residue is larger than the ordinary least square. That means this estimation of your experimental error has gone up. Okay, so it is not a good idea to use a large K. So how small should we choose K? Well, that's our next part of the discussion. But point 6 shows us that the ridge regression estimates can be computed by using ordinary least square approach. You simply choose YA to be this, XA to be this, and then you can work it out to be that. So it can be phrased as an ordinary least square multiple linear regression approach. So the next question, okay, so to summarize, is it a good idea to strengthen the ridge? Yes, because it will help to reduce the variance. But you pay a price, bias is higher, sum of square residue is higher. So we want to choose a K that is good enough for us to reduce the variance, but not too large, so that the bias is unacceptable. After all, we want an accurate beta, right? So how do you choose a biasing constant? So this K is called a biasing constant. So researchers suggested this way. Actually, it's a very simple way. Well, you make a ridge trace. Make a ridge trace. So what is a ridge trace? It's just a plot of beta R versus K for K in the interval. And as K increases, the ridge estimates will vary but stabilize. So we choose some K where the ridge estimates are stable. So here's an example that is described by this one. So this example is, we fit this model. So there are 6 regression coefficients, beta 0, beta 1, up to beta 5. And you can strengthen the ridge to get the 6 ridge estimators. I label them as R0, R1 up to R6, or R0, R1 up to R5. Here I just label them as R1 to R6. And then, now on the x-axis is K. Is K. On the y-axis is the ridge estimator. So for a particular K, you can use this method to find the regression coefficient. So let's say it's 0.1. You can find, and then you can plot a point there. And then you vary to 0.2, you can get another point. You just solve this equation. So the idea is to find these ridge estimators for various values of K, and then you will see a pattern of this sort, where the ridge estimators will start to change quite drastically at first, but then starts to stabilize. It won't be horizontal. You just keep on changing. But at some point in time, where it seems to have stabilized, that would be our choice of K. So it's a little subjective, this method. But that's what the researchers have suggested. Okay? So at this point in time, we know what is a ridge estimator. And to use the ridge estimator, we need to know K. And now we know how to find K. So let's apply this to this data, the acetylene data. Now, again, I'm going to consider unit length scaling. But, you know, if you look at the description of the ridge estimator, there's nowhere that it says you must do unit length scaling or normal scaling or whatever. No scaling is needed to use the ridge approach, ridge estimator approach. But I use unit length scaling for a very simple reason, to help to reduce multi-collinearity, and we have standardized regression coefficient where we can compare. So, unit length means you don't want this. See, SD contains the constant 1 over root of n minus 1. So I remove it by multiplying it. So subtract the mean divided by the standard deviation times n minus 1. So I do that for x1, x2, x3. After that, I calculate the interaction term, x12, x13, x23, and then standardize it. So calculate this first, standardize it. x1 squared, same thing. After I standardize it, I calculate this and then standardize it. So that's how I standardize everyone to unit length. And this is the ridge trace for the acetylene data, right here. Beta 1, beta 2, this 1s, x1 squared, this 1 and 3, and so on. So this is based on the data. So now we need to choose a K somewhere where it starts to stabilize. So here I have chosen it to be, I think I chose it to be even smaller. Here, 0.032. Yeah, subjective. Another person could choose 0.04. Yeah. So never mind. But this is subjective, but results shows that it seems to work. Okay? Now, so that's how I choose. But let me just plot. Since I've calculated the ridge estimator for various value of K, I can also plot the mean square residue for various value of K. So you can see that as K goes up, the residue mean square will also go up, which is not a good thing because we strive to get small residue mean square. R squared, of course, will drop. If your residue mean square goes up, of course, R squared will drop. So it can drop to a very small value. So we don't want K to be too large. So that's the effect. So this table, so I use R. I use R to vary different values of K here. So I start with 0.01. And I find beta naught, beta x1, beta x2, and so on throughout. So each line, it's a model fitted with a different K value. Yeah? And this is the data that I use to plot the ridge trace. So now, you can examine this and see, whether there's any more changes. Looks like it has stabilized. So that's what I am going to use. So Well, so I have described the rich procedure, and I have shown you how to find K for the acetylene data. So burning question is this: how does it perform? Yeah, how does this estimates that we got from rich regression perform as compared with the ordinary least square? Remember, the ordinary least square gave us very poor extrapolated values, right? Negative. So here's an example again. This slide actually is not needed. So let's revisit the plot. So this is where I collected the data, or the data is done for the acetylene data. It's a narrow strip here. This is not the rich, okay? It looks like rich, but it's not rich. They collected data here. Here, all the black dots here. So it's somewhere along this path. So for C is the temperature. Here is the contact time. So the data are collected here. And now let's look at the fitted value obtained using the rich estimators. So here is the observed value for this point, J. And what is the fitted value using the model, using this beta R, 50.01, close. You know, just like ordinary least square. It seems to give us very consistent estimated fitted value, close. Look at this point here, within range of experiment. A bit off, but still not too bad. You can check this A and B also. 15, 14, 17, 16. Close. Now, what about the extrapolated value? Extrapolated value. Sorry, I forgot. I haven't gone to this ordinary least square, the previous one. So here, we don't have data, but the predicted value is negative. This one maybe is okay, and we don't know how good it is. And then D and H, the 2 points on top, both are negative. So this means this ordinary least square model is not such a good idea, because it gives us nonsensical answer. Yeah. Now, what about rich model? So now I'm using the rich estimators. So let's take a look. Again, the data is collected here. Maybe I shade it with yellow now, just to show you that we are doing rich. So same set of data set. So let's compare those that are within the range of experiment. This is observed, this is predicted using the rich model. Close, close. In fact, this point is getting even closer. P, observed, predicted. Close, close. A and B also close. Now how about this point C? This point, we had problem with ordinary least square. But now it gives us a positive value. Here, also a positive value. But are these values correct or not? I don't know. How am I going to find out? I don't know. Okay? But maybe we have a way. Of course, never mind. We'll come to that later. Look at D and H. D and H also positive. So this is a good sign. You compare this with ordinary least square. This is negative. Definitely not. Obviously it's wrong. It's not B is fine. But for rich model, we don't have negative value. The reason is the regression coefficients are now estimated more accurately. So extrapolation also tend to be more accurate. The only problem is we don't know how good this is. So what do you suggest to find out whether this extrapolation is good or not? What do you suggest? I can think of two ways to see whether these are really good or not. Method 1, carry out an experiment at this point and find what is the P, the response. And then compare that with this. If you carry a new experiment at this point and you get something close, bingo, you got a very good model. Carry out another investigation at this point and at these 2 points. And then you feel, you know whether you got a better model or not. Hey, positive doesn't mean it's good, you know. And this is not nonsensical anymore. Yeah? Okay, what's method 2? Anyone? Method 2 is use another method, like a principal component regression method. Do it. And then find out whether these two values are close or not. In fact, that is a tutorial problem in tutorial 11. You are asked to use principal component regression method to find fitted value at these 2 points. If that method, you know, which is a completely different method in theory, give me similar extrapolated values, then I will believe these are trustworthy enough. Okay? I don't even need to carry out experiment. So that's the point. So here is another program to construct the ridge trace, which you can study if you are interested. I know some are not interested, okay? But in case you are interested, you can do it. I know you have competing interests, many courses to take, exam coming up. So I leave that to you. So what have we done today? Today I look at methods for dealing with multi-collinearity. One is to collect additional data so that we can reduce correlation between two variables. Or we can re-specify a model. Instead of using length and breadth, we use area as the regressor variable. And then third way is to use ridge regression. So ridge regression, the idea actually is very simple. We just strengthen the ridge of X prime X matrix to make the matrix X prime X less U condition. Less U condition means what? When I invert it, I don't have this problem of getting large, huge values. And so that's the basic idea of ridge regression. And ridge regression depends on the choice of the biasing constant K. So how do we choose K? We just plot the ridge estimator for various values of K, choose a K where it stabilizes. That's how we choose it. Okay, there will be no more quiz, as I've said, because quiz only goes from week 3 to week 11, as I've stated in my module policy, so I will keep to it. So let's have 5 minutes break. After that, we will look at the other method. I think that is much more exciting. multicollinearity problem. By the way, this morning I just looked at the Facebook and then I found something interesting. Let me show you. There's an airport. I found an airport built in China on a ridge. This is what I saw. Yeah, it's an airport. I think somewhere in Guiyang, if I'm not wrong, built on the ridge. I think for China, anything is possible. I'm very impressed with their infrastructure. It's beautiful. Okay. Let's go on to the study of principal component regression. The idea here is a little bit abstract, so you have to pay a bit more attention if you want to understand it. But once you understand it, actually you will realize that it's quite simple. Okay, let's start. So we have gone through the ridge. So here is a summary of ridge regression and principal component regression. Ridge is a very simple term to understand. And the idea is very simple. We just want to make this X prime X matrix less U condition. And that can be achieved by strengthening the ridge of the X prime X matrix. And in doing so, we have ridge estimators that are biased, but the variance is small. So if the variance is small enough for us, to pay the price of biasness, the overall mean square is small, then it is a better idea. And the acetylene data show that it is quite promising to use a ridge model instead of ordinary least square. Ordinary least square just won't work beyond the range of experiments. So that's how it is. Now, principal component regression has two terms here called principal component. This is not an English word. I mean, really it's not an English word like ridge where we can understand, okay? These two words are more abstract. So to understand ridge regression, we need to understand what is principal component. So that's my job, to help you to understand it, so that when you read the book, you will find that it's easier. But let me just tell you briefly what principal component regression works. How does it work? The other one we know. Very simple. Strengthen the ridge. Now let's read this carefully. When the X prime X matrix is U condition, in other words, near singular, because of multicollinearity. What does that mean? Dependency among variables. Okay? Principal component uses a different approach. Completely different, to reduce the effect of multicollinearity. It's a very beautiful method. Every time I look at it, I fall in love with it again. Yeah. How does it work? Well, it actually, this method is so beautiful. It actually removes the dependency among the regressor variables. It actually removes it. You look at all the variables x1, x2, x3, and so on. Certain dependency is there for the ascertaining data, but you don't know how to remove it, right? But this method gives us a way to remove it, to remove variables that are highly correlated. We can remove it. That's the beauty. And after you remove it, you will get a smaller X prime X matrix that is no longer U condition. Yeah, sounds like magic, right? Well, it is. It is a magical procedure. So let's study how we can remove dependency through the use of principal components. So I'm not going to go fast here. I'm going to go slow so that you can follow and appreciate the beauty of it. Number one, let's take our multiple linear regression model. Y equal to beta naught, beta 1, x1, and so on. P is k plus 1. By the way, this k, usually we use it to denote the number of parameters from beta 1 to beta k, right? Now this k is also used as the biasing constant for the ridge estimator, but they are not related. Because traditionally k is used in ridge regression, but traditionally k is also used here. So I hope you don't get it confused. So this k has nothing to do with the biasing constant. This k is just here. All right, so in matrix form, this is a vector y. This is your X matrix, n times p, including beta naught, and error vector. And you can write this as, you can look at the columns of X matrix and write it out as beta naught, x1, x beta 2, beta 1, beta 2, and so on. Well, we know that this X, there is certain linear dependency, and it causes problem. It results in variance of betas that are very large. So, for example, if beta 2 and beta 3 are highly correlated, one is the engine capacity, one is another variable like engine thrust, they are very highly correlated. So you can remove it. You remove it, there is no more dependency, and it will work beautifully, ordinary least square. So for cases where the dependency is very clear, two variables highly correlated, you just drop one of them. But unfortunately, in many problems, we are not talking about dependency between two. The dependency is among 4 or 5 of them. So there's certain dependency among 4 or 5 of them. You cannot just remove, one of them and hope that it works. It's just like you have a big cancer tumor in your body. You cannot just remove it, And if you remove it all, you'll cause big damage to your body. So how do we remove it? So we need a very good surgical procedure to remove it. So that's the beauty of principal component regression. So now, let's come back to, for this method to work, we need to go back to eigenvalue decomposition. So eigenvalue decomposition says, so first of all, I define the multiple linear regression. Then I assume x prime x is non-singular, which is the case all the time, unless you have two that are perfectly correlated. So x prime x can be written as t times lambda times t inverse, where t is the matrix of orthogonal eigenvectors of x prime x. And this matrix, which is a triangular matrix, has eigenvalues as the diagonal elements. So that's eigenvalue decomposition that I talked about earlier. Well, 3, definition of eigenvalue. So if you have an eigenvalue, it means this. It means eigenvector. You operate eigenvector, you get eigenvalue times the eigenvector. That's the definition of eigenvalues and eigenvector. Now this page I've shown you, I think, the 4th time, but never mind. But this page is the key to understanding principal component regression. As we know, I've gone through this, so I'm just going to go straight to here. So if you have a lambda, an eigenvalue, so you start with a definition of eigenvalue, eigenvector. And if you have an eigenvalue that is almost 0 or close to 0, remember, for x prime x matrix non-singular, all these eigenvalues are non-negative or positive. So if one of the eigenvalues is near 0, then x times this x matrix times the eigenvector will be approximately 0. That means there is a relationship among all the x columns. So if you have 0, you have established a relationship. So we already know. This is a review of what I showed you last time. If you have a lambda j that is 0, then there's a perfect relationship. But in real life, for most data, it's not going to be exactly 0, but close to 0. Then we have near dependency. Now, it is this near dependency that causes the variance of the regression coefficient to explode. So how do we remove that? Yeah? Each one of them, if you look pairwise, the correlation coefficient is small. It's not big. Look at this Goons and Mason data. There is a relationship among the first 4 regressors, but the correlation among them is small. You cannot see it from correlation matrix. So how do we remove this dependency? So let's go to point number 5. So point number 5 will describe the principal component regression approach. So you have to pay attention now. So y is x beta plus epsilon. You got it? Next, write this in terms of the columns of the x. Yeah? Easy to follow, right? Next, I go from here to here. I claim that x beta is this. Okay? Of course can. Because this matrix of eigenvector times transpose of eigenvector is identity matrix. So if you put an identity matrix there, nothing changes. Alright? So now I change to this. So look at this XT matrix. This is what I'm talking about. This XT matrix is this XT matrix. This one. So it's related to this idea. So what's next? So now I'm going to call XT Z. I'm going to call this alpha. Yeah? So Z is xt. X times the matrix of these eigenvectors. So it's equal to this. And so X times the first eigenvector is called Z1. X times the P eigenvector is ZP. So it's a column now. It's just a vector. Well, finally, I can tell you what is a principal component. These columns, all this, they are called principal components. Okay? And, well, something beautiful happened when we derive this Z matrix. We realized that all the P columns of the Z are orthogonal. This can be checked easily because Z is xt. So Z prime Z is transpose times this. And this is X prime X is, X, what's X prime X? X prime X is this one. X prime X is this. So if you substitute that in, you find that it is a diagonal matrix. So that means the columns of Z are orthogonal. So that's one thing to know. So now what we have is we have converted this model to this model. Can you see that? Where the columns of Z are orthogonal. Can you follow me up to here? Yeah? Nothing yet. So I'm just doing a reparameterization. And these are called principal components. They are orthogonal. And what is beautiful is this. Z is xt. Yeah? That means, for example, Z1 is xt1. Zp is xtp. So, according to what I've shown you here, this page, if xt, x times the eigenvector is near 0, then I know there is dependency among the correlation, among the regressors. So all I have to do is look at this. Is this vector near 0 or not? That means I'm looking at a principal component. Is this principal component 0 vector or not? If it is, then I know there is multi-collinearity. You see, I cannot look at this, the correlation of all this, to see whether there's dependency among several variables or not. But I can look at this. All I have to do is look at this. Is this Zp, the last column of the Z matrix, is it near 0? If all are not near 0, then I know there's no dependency problem. But if everyone is non-zero, quite far from 0, except the last one, which is almost 0, then I know there is dependency. You see, by changing the model from X to Z, I can now, the principal component will tell me directly whether there's dependency problem or not. So suppose this one is near 0, then what happened? Alpha p will also be 0, because you don't need that regressor. So now we are talking about p regressors here. So let's just say that if one of them is near 0, this is 0, because we don't need this, then we can just drop this. If you drop this, and let's say all the other principal components are non-zero, then you are in business. You have essentially removed the dependency already, because there is no more regressors that are dependent, so you can remove it. So what do you do after that, if you can remove it? Of course, there's a relationship between alpha and beta. Okay, now, before that, let's come to number 6. Okay, alpha is this. Alpha is the parameter, regression coefficient based on the principal components. So you can see that the variance of all these regression coefficient is actually dependent on the eigenvalues of X prime X matrix. So, in other words, variance of, let's say, alpha p. Alpha p is 1 over lambda p. If this is near 0, then your last principal component will be near 0, and you have a large variance. You see? So, if you can remove, so if I know that lambda p, for example, is near 0, then if you don't do anything, then the variance will be very large. And if lambda p is near 0, that means this quantity will be a 0 vector, a near 0 vector. So, if it is a near 0 vector, we can remove it. That's how you remove dependency. Okay, so here is a summary of principal component regression approach. So number 1, so I'm going to summarize everything now. Number 1, assume the regressor variables are arranged in the order of decreasing eigenvalues. When you use the R function eigen, you will arrange it in this manner. So just nice. Secondly, you can reparameterize it in terms of the principal components. And now, point 3. Suppose the last S eigenvalues are near 0. Suppose, let's say, the last 3 or the last one. Yeah? Then, how do I know it's near 0? Because I can check. I can check the matrix. Now, if this is near 0, that means there is some dependency. See, according to what I've described to you, that page that I showed you 4 or 5 times already. If this is near 0, that means there's dependency. In other words, if a principal component is near 0, it shows that there is dependency. So what I'm saying here is, the last S columns are near 0. Alright? So this matrix will be ill-conditioned because the last S columns are near 0. Imagine you have a regression model where the last S columns of the X matrix is all near 0. You have a problem because the last 4 are 0. You create a problem. So what you do is, so the way principal component regression does is, you set the last S column to be zero vector. They are near zero. So you just change them to zero. And the associated regression coefficient will be zero because you don't depend on those regressors. So they must be zero. So after you set all those to be zero, right, you are now left with a smaller model, P minus S, up to here, P minus S. Now all these are zero. From this point on, they are all zero. So you remove them. So these are all zero now. So you're left with this model. And this model, all the z's are non-zero. Non-zero means what? No evidence of dependency among the regressor variables. So the idea is, you see, you convert your model into another model based on principal components. You can now see clearly which regressor give you problem. Those regressors that are near zero give you problem. Throw them away. And you'll be left with a more compact model, smaller model, that has no dependency problem. And so you can now do a regression like before and estimate this value. Estimate all this. And after you have estimated all this, the rest are all zero, right? So you can estimate all this based on the non-zero principal components. So this is done like before, and then later you can retrieve back the beta. So T times alpha of PC, you get back the original. So beta is based on the original Y and X model. And this is your principal component regression estimates. You get that? So, that's it. And so I hope you understand what I say. You have understood what I say. The idea is this. Let me just say it one more time as summary. So we start with a model. This one. And they assume there's some dependency. Even if there's no dependency, you will find that all the principal components are really quite different from zero and you have no problem. Okay? So you change that model to this in terms of principal component. Now what is principal component? Principal component is this one. Z, P, for example, is X times TP. So let's look at one of them. So according to our analysis, if this is a near zero vector, then there is dependency. So once you convert all these into principal components, all you have to do is to check the Z column. Is there any column that's near zero? If there is, then there's dependency. If all are different from zero, then there's no dependency. So suppose this is near zero, the rest are not, then you drop this one out. Do a regression coefficient on the rest to find alpha 1 and alpha 2 and so on up to alpha p minus 1. After that, you can find beta from here. And that is your principal component regression coefficient. You got the idea? So this method actually throw out all the dependency, do the regression, get accurate regression coefficient, and then go back and find beta. Okay, I will continue with the discussion of principal component regression this coming next week. Okay, so I'll stop here.
Yeah, maybe if you go to a 7-Eleven. You know what? Martin has things that's like anything to do for the good girls. It's like, yeah. I don't know, man. They got something to do.